Assalamu alaikum. My name is Mohammed Jamshid and I am from second semester Mechatronics Engineering at university. Today we are going to solve some examples of the diode combination with the resistors and any battery. Uh, Before starting the lecture, I'm going to tell you that what is diode. Diode is basically a junction of p-type and n-type semiconductors which allows the current to flow in one direction and opposes the current to flow in another direction. It has some when it is forward biased when the positive terminal is connected to p-type and negative terminal is connected to n-type. It is forward biased and if it's opposite, then we call it reverse biased. In forward bias, it behaves as short circuit, and in reverse bias, it behaves as open circuit. And when it's forward biased, it behaves as short circuit with where practically it drops 0.7 volts for silicon diode and 0.3 volts for germanium diode to allow the current to flow through it. Here is the example where we have to find V naught, I naught, and V naught, I1, ID1, and ID2 for the parallel diode configuration. In this given circuit, you can see that there's the 10 volts battery, a resistor of 0.33 kilo ohms, and two diodes that are in parallel. As I have told you before, that you can see that the positive terminal of this battery is going to connect to the positive side or p-type side of the silicon diodes and of these baud diodes. It means that these baud diodes are forward biased and they behave as short circuit with 0.7 volts drop. Uh, from this concept, we can conclude that the voltage V naught would always be 0.7 volt as the diode is forward biased. So we have concluded that V naught is always 0.7 volts. To find the current through this resistor or the I1, we can find it by the from the formula that the total voltage by applying KVL here, as the total voltage is 10 volts and the voltage through this the diode as both are in parallel, they are 0.7 volts, so 10 minus 0.7 gives us about 9.3. It means that the voltage across this resistor is 9.3 volts. And if we use V equals to I divided by V equals to IR and I equals to V divided by R, we get 28.18 milliamps. And as these both resistors, both diodes are connected in parallel, the current will divide here from this node, from this common node to these two branches of the same value. And if we divide the current passing through this resistor divided by 2, it gives us the current from the one branch of diode, whose value is 14.09 milliamps. Let's check its Proteus simulation of this circuit. The same configuration has been made here. If I run this, I can see that the resistor is having there here a drop of 9.48 volts, and the current passing through this resistor is uh, 28.7. And then from this node, I can see that the current is dividing into two branches equally. Here 14.4 and also here 14.4, and here as the diode values differ practically, here the its actual value is 0.7, but here it shows 0.52. I hope that this problem would be clear. Let's move to another problem. This is the example 2.26 of the bolstered electronics. Here we have Zener diodes. Zener diodes are the diodes which only work in the reverse direction. When they all of the different there are different types of Zener diodes with their different voltage breakdowns. with the different breakdowns. Breakdown voltage, which means that it only starts working, when it's forward biased, it behaves same as a normal diode. But in reverse biased, this Zener diode becomes forward biased and behaves as a forward biased. I mean that it allows the current to flow through it when the voltage approaches to its breakdown voltage. In the given example, its breakdown voltage is Vz equals to 10 volts. The question given is that for the Zener diode network, determine VL, VR, IZ, and PZ. VL is the voltage across this load, VR is the voltage across this resistor, IZ is the current passing through that Zener diode, and PZ is the power of the diode. Here I can see that if to do the analysis, I have to remove this load to check that how much the voltage the whole circuit is giving to across this point and this point. I have removed the load, and then when I apply KVL or another, let's say voltage divider, as there are two resistors and the voltage is and there is a source, voltage DC voltage source. The voltage has been divided. The divided voltage across this R load I have to find from this voltage divider is 8.73 volts. The voltage divider formula is written here, and then by putting these values, when I have found this V load, this V load would be as this load and this diode are in parallel. The voltage across V load, which I have said as VL, would be same as the voltage across this Zener diode, which I have called V here. You can see, which is also 8.73 volts. As I've told you before, that the Zener diode only starts working when its breakdown voltage is reached. Here you can see that here you can see that its breakdown voltage is not as its breakdown voltage is from this graph. You can conclude that its breakdown voltage is 10, and the voltage there, which is known as V, is 0.73 volts. Sorry, 8.73 volt. It means that the Zener diode is still off and behaves as open circuit. The current passing through the Zener diode is IZ equals to 0 ampere, and by using the formula of power, Pz equals to Vz Iz, as P equals to Vi, it gives us 0 watt. The thing here is the KVL applied to find the voltage across that resistor. We at this mesh, if we apply this loop, we apply KVL. Here it would be 16 volts minus this 8.73 volts across this diode. It gives us 7.27 volts. It means that the voltage across this resistor of 1 kilo ohms is 7.27 volts. We can also find this voltage by this formula if we replace this RL by R. Its second part says that repeat part A with RL equals to 3 kilo ohms. It increases the value of this resistance RL as it was before 1.3. Now the question says that change it to 3.3. 3 kilo ohms. We apply the same method. First we remove that Zener diode and apply voltage divider. From here we can see that it's 12 volts. The voltage here would be same as this voltage. It means that the voltage across that Zener diode is also 12 volts, but is also 12 volts, as it is greater than the breakdown voltage of that diode. The diode will get on and behaves as a short circuit. So as the voltage across it would always be 10 volts. VR equals to VI minus VL equals to 16 volts minus 10 volts. Same method, we are applying KVL here. And the current through the load would be 3 amperes, that we know the voltage there. It is 10 volts. And here we have found this voltage just to check that how much voltage at that branch or that place, that open circuit, our battery and other resistors are giving. It is 12 volt. It means that the we just use this value to conclude that whether our diode is in off state or on state. Now by using simple Ohm's law, we have found these all the things. And at last we have found here we used KCL, Kirchhoff's current law, that the current entering and leaving the nodes are always equal. Now the current through the diode becomes 2.67 milliamps, which is less than and its power is 26.7 megawatts. Sorry, milliwatts, 26.7 milliwatts. We are also going to check its Proteus simulation. First with the given values of part A, and then doing the illustration from part B. Here you can see the resistor of 1.2 kilo ohms is used. So as you can see here, the voltage here is 8.73, which doesn't turn this diode on, and current passing through this is always 0. If I change this value to 3 kilo ohms, now you can see that the voltage here is 10 volts and this diode has been turned on. So these both configurations have been proved with the Proteus simulation. Now we are done with today's lecture. Thank you so much. Allah Hafiz.